Hello, I'm Matthew Hunt, a computer science major, and I did research under my faculty mentor, Christian Shelton, on improving readability, organization, and speed in a machine learning code base to estimate redshift and detect damp Lyman alpha absorbers in quasar spectra. So I have a video here that shows the quasars in our galaxy, or in the universe, send off a lot of light and have their own spectrum that usually has a peak orange blue. And due to the expansion of space, or just traveling through and hitting different clouds of gas, such as a damp Lyman alpha absorber, they have dips and and by the time that they get over to what we observe them with here on Earth, they're redshifted over. So what we need to do is that we need to redshift them back into their original position to really understand the structure of the universe a lot better. So a lot of where these quasars are held is on a catalog called the Sloan Digital Sky Survey website, with 2.5 million plates and spectroscopy results stored there. And there's also stored there is some redshifts that were calculated using visual inspection, which is the primary method originally used to calculate these redshifts, which just means that someone went in by hand and calculated them. And there's about 500,000 quasars per catalog in this website that is stored and used. So a lot of data that needs to be analyzed, which really works well with machine learning and computing it using a code base. This code base was originally in MATLAB and used a machine learning model known as a Gaussian process to calculate the redshifts and detect damp Lyman alpha absorbers that the quasar lights went through when they went through them. And it originally combined two different estimations known with the quasar redshift as well as the DLA detection itself. And by combining those two, it saves a lot of work and puts the process down to about a week or two instead of possible months when done through a visual inspection. And this code base is still slightly unoptimized, which is where my research came in, which had a goal of translating this existing quasar redshift and DLA detection code base into Python. There's three major reasons that I needed to do this. And one was that it was moving from a proprietary language of MATLAB to an open language of Python, meaning that that researchers would have to pay money or join the subscription for MATLAB and using it over Python, which you just need to easily install the libraries and then go ahead and use. As well as the next thing that I did was restructured it to make future modifications easier by putting different parts of the code as well as the scripts into a form that are much easier for researchers or astronomers to analyze. And then putting them in classes as well ideally makes it a lot easier to understand than the README file, which was originally a lot more confusing in the original code base. So this helps facilitate future work to improve speed and accuracy even further in calculating these quasar redshifts and DLA detection probabilities. So to understand the research, you have to first look at the flow of the code base, which has three major steps. The first step is downloading the data from the website, which downloads all of the quasar data into a file structure on your local machine with the catalog data and the different quasars for the 297,301 quasars directly there. And then it takes this and learns the Gaussian process model, which is kind of like a Gaussian distribution in statistics with to get the best weights for the redshift and DLA estimation that it would use so that it would be able to calculate it with a lot more efficient speed. And then it takes the Halton sampling sequence, which is an important sequence of numbers used to estimate and test the quasars, and puts it together to get a result of testing the model, which really is calculating the probabilities of the DLA and the redshift of the DLA and the redshift of the quasars, and comparing it to the visual inspection values originally in the catalog themselves. So some improvements that I made to the code organization was I improved the set parameter file usage and creation, which had to be constantly loaded in MATLAB. So by streamlining it and having it run in the scripts, that was less of a hassle to deal with, and can be just done straight up and fully instead of at each step in like the original README in the Codebase said. And I also used different Python libraries, which to approximate some of the functionality in the MATLAB, such as wget, astropy, and scipy to read things like FITS files, which the spectroscopy results and all the parts for the quasar are stored in, and also to help approximate the matrix calculations that MATLAB is really strong at doing, since there's a lot of matrices that you deal with in this code base. I also made the organization more object-oriented in like classes so that it's usually easier to group together the different parts of the modules that need to be run for this code base to work as well. And after working on code organization, I went on to optimizations of the calculations themselves, with opening and closing files being one example, which had problems with crashing and the like, which means that I had to go back and purposely close each file handle after using it so that all the quasars could be loaded in before any of the problems would happen in the downloading part. And then after that, I had a major problem with the learning code minimization, which really was improving the model. And we eventually decided just to have it 1,000 iterations instead of 4,000 iterations in the MATLAB. But that involved using a timing table, which I show here, with pre-compilation versus interpretation, with the pre-compiled version using a library known as Numba and Ngit to pre-compile, which is a lot faster than interpreting a programming language on your computer. So I tested it out, and pre-compiled usually did better, as well as not using a Cholesky decomposition, which is basically was just a simpler method to reduce the amount of time that the learning code took for each iteration, and that also ended up being more helpful for the Python version, since it couldn't take full advantage of that shortcut as a MATLAB version could. And some other options were also ruled out, such as using tensors and GPU calculations, since that ended up taking extra time to translate them into the form that the GPUs could process as well. And so that's the main part of for the learning code. And for the testing code, the major optimization I did was related to the void profile and using some pre-compilation as well. And the void profile was originally pre-compiled in MATLAB as well, since it was a major time sink for the timing of processing each quasar. And just to give an idea, it takes 10 minutes to test and process a quasar in the MATLAB version, and in the Python version, before I made the optimizations to it, it took about an hour and a half per quasar, and reduced it to about 45 minutes per quasar. And I did that to using a one-dimensional interpolation, which is just using a lookup table instead of having to go through the function, and that approximates this equation here. And so after running 1,589 quasars through the testing code for both, I compared the redshift accuracy, the DLA redshift accuracy, and the existence of DLA probabilities between the MATLAB and the Python version, and learned that the redshift calculations as shown in this graph are all usually faithful to the MATLAB, except for one outlier, maybe possibly due to a bug, since it's closer to 0 here as the absolute difference. And the DLA detection did worse with 80% accuracy, with a lot closer under the 0.25 difference in estimations, with some of the guesses being the complete opposite than compared to the MATLAB code. In terms of the DLA redshift, there is some better accuracy as well, with less than 20% of it being a problem, showing that some of the problems in the existence of the DLA may not necessarily be the fully relevant ones compared to the true values gotten by visual inspection. So the conclusions is now that the doorway for future work is much more open with this code base, now that it is no longer in a proprietary language and is in Python. And there are also some possible reasons for the 20% error. One is that the learning code is different, and as I mentioned before, it stopped at 1,000 iterations for the Python version instead of 4,000, since it took about 10 days for 1,000 iterations, and it took about 20 days for 4,000 iterations in the MATLAB in comparison. And another one is that the Holton sequence is different between the two, which was important for estimating the values in the testing code of testing the Gaussian process model. And another problem that could possibly show up is that the different quasars could be less stable, unlike this graph, which shows the flux and the wavelength of one quasar subscribing to the model pretty well. So it is estimated pretty well. And there's also the consideration that the MATLAB was worked with multiprocessing better at the time, which could lead to some differences as well. So here are my references, and some anticipated questions is, how did the Python code finish in time if each quasar took 45 minutes? Is that I split up the 1,589 quasars into 16 jobs that ran at the same time, which means that 16 quasars were being processed at the same time, which reduced the time to about 5 days for the 1,589 quasars compared to the MATLAB, which took 11 days for the full version. And what were some of the difficult parts to translate from MATLAB to Python? There's a lot of difficulty with downloading the libraries necessary for the minimization, and then not working with Python. So having to use some libraries to approximate with slightly different results was necessary, as well as understanding the README, which had a lot of code that needed to be loaded into memory, such as the set parameters, which I fixed up, and provided some problems, as well as having to go back in future scripts to earlier parts to fix up errors that propagated in future areas as well, like switching from Python 2 to Python 3. What was frustrating about the original code base that was fixed in this new one is there was the README was definitely difficult to understand, and there was about 8 or 9 scripts that had to be run in total for the MATLAB code to get and finish up testing all the quasars, which is now reduced to only 5 in the Python. And it was also frustrating making sure that the speeds were, that all the stuff had to be loaded in beforehand as well, which is a lot more streamlined. And the scripts are also a lot easier to comprehend and understand now in the newer one. And the last question is, why was this research important? Understanding our structure of our universe really involves understanding and calculating these redshifts and getting their values in the quasars, and having the best method be the just manually visual inspection is not very good, especially when there's both the power of computers as well as with like 500,000 quasars that come in every year, which need to be really understood and dealt with appropriately. So having any improvements that help researchers use this and helps facilitate future work, and seriously helps us understand our universe better. And that's my presentation. Any questions?